Hello chemists, this is Ms. Placino and you are watching Screencast 2.4, An Introduction to Quantum. Today we're going to talk about how the new understanding of the electron changed the model of the atom. If you watched Screencast 2.3, hopefully you took away that the electron behaves in a really bizarre manner, unlike anything scientists had seen or had even been able to predict at that point in time. So thanks to this new understanding of the electron, the model of the atom had to change yet again. Just to quickly recap the different models that we've seen. We started off with John Dalton and the billiard ball model, which basically just stated the atom is a hard round sphere. J.J. Thomson discovers the electron. He says, okay, the atom itself is positive, and then there are randomly scattered electrons throughout. This is called the plum pudding model. Ernest Rutherford conducts his gold foil experiment and discovers the nucleus, a small, very dense, positively charged mass at the center of the atom. We've just got the electrons hanging out wherever. We learned that energy is quantized. So Bohr gives us the Bohr model or the planetary model. Pick one, doesn't matter. Where the nucleus is still at the center, and then you have orbits, which are basically paths where the electrons can orbit around the nucleus in. And we find out that this only works for hydrogen. Scientists perform the double slit experiment and find out that the electron is really, really weird. So they have to propose a new model, and we call that model the quantum mechanical model. And in this model, we'll see the nucleus is still at the center of the atom, but instead of having orbits or paths or whatever you want to call them for the electrons to occupy, they occupy these electron probability clouds. So you get a very hazy picture of what the atom looks like. We're going to work really on understanding the basics of the quantum mechanical model today, things like energy level, sublevel, and orbitals. And we'll build on that in following lessons. Let's take a look at the do now. Explain the cartoon based on what you know about the behavior of the electron. Take a second, pause the video, see if you can figure it out. Basically what we have here is a horse race that looks like it's ended in a tie. So they check the electron microscope to see who actually has won. And then the scientist is upset. He says, no fair, you changed the outcome by measuring it. And I'm asking you to relate this back to what you learned about the electron in the previous lesson. Hopefully you remember in the double slit experiment, scientists were trying to figure out if the electron behaved as a particle or as a wave. When they didn't really observe it and they just saw what happened after the electron passed the double slit, they saw that it behaved like a wave. When they tried to peek and observe which slit it was actually going through, then the electron started behaving as a particle. So simply by observing or measuring the outcome, you can actually change the way something behaves. And that's really what this cartoon is getting at. If you watch a lot of, nerdy cartoons, you'll notice that there are quite a few shout outs to the quantum mechanical model. So let's get into that model of the atom. Erwin Schrödinger proposes the quantum theory, which mathematically describes the wavelength properties of electrons. Basically, he took Louis de Broglie's theory and he made some small changes to it, and it kind of took care of some of the weird anomalies that de Broglie couldn't explain with his initial theory. And he also takes into consideration Heisenberg's the electron as a particle theory. So the equations that he comes up with treats the electron as a particle whose location and speed can be discussed in terms of probabilities. If you remember, the wave theory says that you can know the exact location and speed of an electron. And the particle theory, Heisenberg's theory, also Heisenberg's uncertainty principle, says that you cannot know the speed and location of the electron. The more you know about one, the less you know about the other. So Schrödinger came up with these mathematical equations to describe where we might possibly be able to find an electron. So let's talk a little bit more about the quantum mechanical model. And again, we're just going to cover some of the basics today. So we'll start off with the principal quantum number, which basically is going to represent the distance from the nucleus. So you can kind of think about this as being very analogous to the Bohr model of the atom, where you have your nucleus, and then you've got the different rings going up from there. The farther and farther away you are from the nucleus, the more energy that electron would have. So for example, an electron sitting in the first energy level is going to have less energy than an electron that's in the third energy level. Just like in the Bohr model, those rings are different sizes. You can think about these energy levels as being different sizes. The ones that are closest to the nucleus are going to be smaller, so we're not going to be able to hold as many orbitals. And you can just think about orbitals as being electron clouds at this point in time. Let's talk a little bit more about the orbitals. Each orbital can hold a total of 2 electrons. So we're going to show you some pictures of the orbitals, and they take on some really wacky shapes. Don't be fooled, doesn't matter how complex they look, every orbital out there can only hold 2 electrons. Orbital shape does not change, but size does. The greater the principal energy level, the larger the orbital. So for example, we have s orbitals that look like spheres. I have a 1s, I have a 2s, and a 3s sublevel, and consequently a 1s, 2s, and a 3s orbital. They're all going to have the same shape. They're spherical, but as you get to larger and larger numbers, you're going to get to larger and larger orbitals. So again, the shape stays the same, but the size is going to increase as you get further and further away from the nucleus. Or another way of saying that, you end up with a larger principal energy level, or a greater or higher principal energy level. Here are all the orbitals you need to know. I know it looks a little overwhelming. You've got 4 different sublevels: the S, the P, the D, and the F. And within each of those sublevels, you have some very uniquely shaped orbitals. These orbitals, again, they're just kind of like clouds where you have a chance of finding an electron. And these shapes have been predicted by solving Schrodinger's equations. Very heavy, intense math. Again, we're not going to do that at this point in time. We'll leave that for college. So in the S sublevel, you have 1 orbital. It's spherical. And the P sublevel, you'll have these 3 different orbitals, and they have I guess a shape kind of like a figure 8. They're just oriented in different ways in space. The D sublevel, most of them kind of look like 4-leaf clovers. And you have this weird guy, kind of looks like a figure 8 with a donut around the middle of it. The F sublevel, things get even stranger. You've got those 4 that I guess kind of look like flowers, maybe. And then you've got these 3. And I don't even know how to describe those shapes. But again, they are all determined mathematically by solving Schrodinger's equations, wave functions. Here's another way to represent those orbitals. You'll notice in all of these pictures, especially let's look at like maybe this part right here. The electron density is greatest near the nucleus and decreases as distance increases. So the way that's represented in this picture is through light intensity. The brighter spots are supposed to represent areas of high electron density, and the dim spots represent areas of low electron density. And you can see the general pattern is very bright at the center, and then getting increasingly dim or less bright as you move further and further away from the center. In some places you have like complete black, just complete darkness. That means that electrons cannot exist there, and we call those areas nodes. There are different nodes in different orbitals. I don't want you to worry too much about that. What I do want you to know is that there is one place in the atom that is always going to be a node, regardless of what sublevels and orbitals are present. Any guesses? Hopefully you're thinking the nucleus. We know that the electrons cannot exist in the nucleus. And all these orbitals represent, and just that 90% chance, chance of finding an electron. We have just a 90% chance and not a 100% chance because, according to the Heisenberg uncertainty principle, you cannot know the location and the speed of the electron simultaneously. So we have to talk about where the electron is in terms of probability. If you take a look in your workbook, you've got this chart, and I want to take just a minute or so to fill it out. And let's go through this together. So in the first energy level, we have the S sublevel. If you look back at that picture of all the orbitals, how many different types of S orbitals are there? Hopefully you're seeing that there's just one. The number of orbitals in the energy level. Well, there's one S orbital, and there's only one S sublevel, so I'd say there's one orbital in the energy level. The number of electrons per sublevel, well, each orbital can hold 2 electrons, so I have 1 orbital, so a total of 2 electrons. And finally, the number of electrons per energy level, well, it's the same. It's 2. In the second energy level, we see S's and P's. If you look at the chart, there's only one type of S orbital. If you look at the chart, you can see that there are 3 different types of p orbitals. So the total number of orbitals in that energy level is 4. We know in the S sublevel there's a total of 2 electrons, as each orbital can hold a total of 2. And in the p sublevel we have 3 orbitals. 3 times 2 gives me a total of 6. That gives me 8 electrons in all that can be held in the second energy level. Go ahead and see if you can figure out the third and fourth energy levels on your own. And I'll give you what sublevels are present. So pause the video, see if you can figure it out. Use the orbital diagram if you need help. So in the third energy level, S, 1 orbital. Our P has 3 different orbitals. Our D, looking at the diagram, has a total of 5. So the total number of orbitals in that energy level is 9. Electrons per sublevel, 2, 6, 2 times 5 gives me 10. That's a total of 18. Using the orbital diagram from your workbook, there are 7 different f orbitals for a total of 16 orbitals within that sublevel, or within that energy level. The number of electrons per sublevel, well, it's going to be 2 times each of these numbers. So I have 2, 6, 10, and 14. If I add all those up, I get 32. Kind of cool when you look at this to see that the energy level, the number of electrons per energy level breaks down the same way that Bohr predicted. So to wrap up, I'd like you to take a minute to try to write a 2-sentence summary of today's lesson. I really advise trying to do the practice problems that are in your workbook. We're going to worry about electron configuration and how exactly the electrons are going to fill up the different energy levels and sublevels within an atom. But for the time being, you should really focus on just kind of understanding the basic rules about which sublevels can exist in each of the energy levels, how many total electrons can be held within a sublevel or an orbital, and just really try to practice with that. They're in your workbook and they're definitely on the Quest homework as well. All right, that's it for today. Thanks for tuning in.